Thank you very much. I'm Alexander Dijkshoorn from the University of Twente, and I would like to present you the work I did for my master thesis on characterizing the electrical properties of 3D printed anisotropic conductive sheets. First, I'll give you a short introduction on the problem. I'll show some previous work, and then I'll talk about the methodology and the results I obtained from the methods I applied. The field of 3D printing transducers is currently growing. And already examples exist of printed force sensors, for example, piezoresistive sensors or capacitive force sensors, but also, for example, EMG sleeves, like the one shown on the top right. For these methods, a lot of times fused deposition modeling is used. A 3D printing technique in which an extruder extrudes a molten line of plastic onto a build plate, line by line, layer by layer. And with this method, it inherently introduces some anisotropic properties into the 3D prints you make because of the layered line-wise methodology. To improve the printed sensor design, we would like to have a better understanding of the effects of this printing technique and to study this anisotropy in the electrical characteristics. In the method, I only considered horizontal 2D sheets, where we modeled the thing as so-called track elements, traxels, which are the printed single lines. In literature, already a model exists for this, which is, only looks at the resistivities and considers a different resistivity in every direction of the print. For this method, I use an extended model and FEM simulations to simulate this. Furthermore, for the experimental methods, currently, sensors are characterized by means of their impedance, so a global impedance measurement is performed. However, we would also like to consider the voltage distribution and the current distribution in our samples. And for this, we applied two methods from different fields of research. First, the voltage contrast scanning electron microscopy, where with a scanning electron microscope, you look at a sample and the local voltage influences the intensity you measure. So depending on the measured intensity, you can relate this to a voltage locally in your sample. And we use the infrared thermography, where we measure the heating of the sample by means of Joule heating with an IR camera, infrared camera. So for the model, as I said, we use an extended model for AC cases with fused traxels, track elements, where we use bulk properties, so the bulk permittivity and the bulk resistivity, and we use contact properties between the printed lines, so a contact resistivity and a contact capacitance. Furthermore, we look at two cases, samples with leads on the opposite sides and sample with leads on the same side for this study. With the simulations, we did the finite element simulations with the console software, where we have a sample on which one end we apply a voltage and on the other end we ground the sample. And as you can see, depending on the parameters you have some anisotropic voltage distribution throughout your sample. And depending on the parameters, so depending on the ratio of the bulk and the contact parameters, and depending on the frequency of our signals, we can have either really isotropic conduction, where it goes from one corner, the conduction goes from one corner to the other corner, or we can have very anisotropic conduction, where the current mainly flows through the traxels throughout the structure. For the fabrication, we used a commercial printer, a flash force, in combination with the carbon black filled thermopolyurethane, which is like a rubbery material with carbon nanoparticles inside. And we printed it on a glass wafer for the two types of samples, and we connected leads by means of copper tape and silver paint. The samples you see right here are about 15 by 15 millimeters wide and long and 200 micron thick. The first step in the measurements was a global impedance measurement, the status quo for current measurements, with a gain phase analyzer by means of a 4-point measurement. And we could use these measurements to fit the model parameters. The measurements give quite good results in the range of 1 kilohertz or 100 hertz to 1 megahertz. Where for the higher frequencies, deviations occur because of the parasitics in the coaxial cables. With the fitted parameters, we could move to the next measurements method. For the voltage contrast method, the important thing is that depending on your bias voltage of your sample locally, the amount of electrons that end up in your detector is different. So for negative voltages, almost all electrons are accelerated towards your detector, so you have maximum intensity. However, for positive bias, a part of your low energy electrons do not end up in your detector, and in this way you can really map from your intensity towards your voltage. We could use this by making a calibration curve. So we applied the same voltage to our entire sample, measured this step by step for different voltages to reproduce this curve, and then filter it, and then pixel by pixel we had a similar curve, and we could fit this, invert it, and apply it to our measured intensities. So for example, we have a sample with on the one hand 10 volts, on the other hand 20 volts. As you can see, there's a change in intensity over the sample, and we could use these curves to get the voltages everywhere. Results look like this. We have quite good results qualitatively. These are the respective FEM simulations, and these are the measurements where you can see that the voltage is almost isotropic. That's because the printer is actually quite good in fusing the horizontal tracks. For the other method, we used infrared thermography, where we study the Joule heating in the sample, so the power dissipation, by means of measuring the infrared with an infrared camera. Qualitatively, we get quite comparable results, where you can see that in the connections, there's most of the dissipation, and on the edges, there's also some dissipation. However, we would still like to extend this with a better modeling of the temperature, because the coupling, it's a very indirect method. So the power dissipation heats up the sample depending on the heat transfer around the sample, which is then radiated by infrared light. However, there's quite some thermal diffusion in the sample, smoothing the pattern we measure. So modeling the temperature would be better in this case, give better results. All in all, we've presented a model which can be used to predict the conduction in 3D printed samples for different parameters and frequencies. We've applied the voltage contrast method for qualitative and quantitative analysis of our voltage distribution in combination with the infrared thermography, for which we can now use for solely for qualitative measurements. And we still need this temperature model to also get a better quantitative idea of what's happening. But all in all methods together correspond well and give us a clear view of the electrical conduction in 3D printed sheets. Thank you very much. Are there any questions?
Thank you.